Okay, so we're live. Yeah, okay, 1:30, we're good. The so today we're going to be tackling two different subjects. I'm going to actually post them as two separate lectures. One we're going to move through quite quickly. It's more of a formalism. I think for a lot of you, you've seen this before, so really hope that this is just a review and it's just kind of a statement that we're all on the same page. And the second one, we are maybe going to move into some new stuff for a lot of you. And that's going to spill over into the next lecture as well, and not just today. Okay, I should be clicking something. Okay, so I want to make sure that we're explicit on how we're understanding structures of molecules. And we touched on this last class, but I want to have some more thorough notes on that. So there are multiple ways to write chemicals. I don't really know what else to say with that. So one option are complete Lewis dot structures, the way we've drawn them. You can do kind of this, I call it like the Lewis line structures, where we replace, the two dots between the carbon and hydrogen with a line, because a line is faster to draw than two dots. Or we can write condensed structural formulas where we shorten that whole thing up, and we're trying to lots of different kind of compromises in between the two. So we have three different representations of the same structure. One where we have written it all in letters, one where we've indicated that we have bonds, and one where we indicate that really these are two different ethyl groups, CH3, CH2 groups, dangling off of a single oxygen. All four of these representations are completely correct. They're also a little slow. So let's say we have, I don't know, draw a Lewis dot structure. And I need to remember my lone pairs on oxygen. And so it's a full Lewis dot structure. That's equivalent to writing that. It's equivalent to writing this. It's equivalent to writing, oops, I got a little carried away with my equal signs there. Or that. Those are all exactly the same way to write, different ways to write the same thing. All of those took way too many pen strokes for me. So my preferred is, as we were discussing last class, each line represents a bond to a carbon. Yeah, I'm dropping them on those structures. I started moving away from the lone pairs on those. They're still there. I'm trying to think. I go back and forwards every year, depending whether I want people to put them in by default or not. How about for now we put them in by default? We'll keep track of lone pairs. Yeah, and it's the same as the Lewis structure. All these things are absolutely identical. These are all absolutely the same molecule. They're just drawn different ways. It's just this way here is much faster. Many fewer pen strokes. And so that's what we're going to be moving towards, is drawing them like that. This is called a line angle formula because it's made up of lines and angles. The one thing to keep in mind, and I think you guys remember all this stuff. Yeah, for now, let's show the lone pairs. Because the evaluation for this course is going to be on the final exam, is going to be the one time when you're going to be drawing brand new things and submitting them. We'll discuss that ahead of the final exam where people want to be. I don't really care. What I do care, though, is that if you don't draw them for now, you can easily lose track of electrons, and you can lose track of charges, and you can start drawing some things which aren't realistic. So I would draw in all the lone pairs at this point. So we can have other types of molecules, of course. I'm not going to draw the Lewis structure. I'm going to just stick with these line angle, the Lewis line structures. So you can have this molecule. This is acetonitrile. It is a very common solvent. And I can draw that out as CH3CN. Note that I'm implying a triple bond between, for the complete Lewis structure, we just leave the H's out at the end of the line. This line angle formula, you can leave the H's out. The general rule, though, is if you're writing in the letter C for carbon, you have to write an H for hydrogen. If you just use a line, you do not need to write it. Because if you're doing the line angle formula, we assume that you put in the right number of hydrogens. So that's our rule. So in this case here, you have to figure that out, and you're looking at this middle carbon here, and it's got no hydrogens on it. And so it still must be making 4 bonds. So it has to make 4 bonds between the carbon to its left and a nitrogen to its right. And it can only possibly make 1 bond to the carbon to its left because this carbon already has 3 bonds to hydrogen. And so it must be making 3 bonds to nitrogen. So that's why this is all the same. Or I could write it like and stick a dot in the middle there, I mean carbon. The reason I'm not doing an angle on that line is because that's a very straight bond. We'll come back to why that's straight. But it's 180 degrees. It's got to be straight. And so I can put a dot in there to represent the carbon. Yeah, I don't think this is, I hope this is review for a lot of you, and I hope a lot of you have seen some line angle formula before. In general, these are the rules. We do have to explicitly draw every atom that isn't carbon and hydrogen because based on our formalism, we think that they're either carbons. We think any vertex is a carbon. So if it's not a carbon, we have to indicate if it's a nitrogen or oxygen. The only time you draw hydrogen is if it's bound to a nitrogen or an oxygen, because you do need to say how many that is. And lone pairs are generally not drawn, but we will. Because when you're drawing them out, it's not needed officially, but for this course, I think to make sure that we're constantly on pace and we're making sure we're keeping track of our electrons, we should probably draw them out. Go. So let's think of a few possible examples. So if we have so we had this molecule here. No, you know what? I like fluorine. That takes a lot of pencil drawing. It's a lot of drawing. So if we try and draw that out using a line angle formula, what we generally want to do is we want this angle to be about 120 degrees when we're drawing it. And that's just because it's a nice angle. It's not because that is the bond angle. The bond angle is not 120. We're going to come back to it's 109. But for drawing, it's convenient. So ideally we want that. And so we often want to draw these horizontally. Doesn't matter too much. But what I normally want to do is I want to draw the carbon chain as a zigzag. And zigzags are fun. So if I label these guys, I'm just going to label, I've learned my lesson. I have to click with my mouse to change my color. And then I click a color. I don't like blue. It reminds me of an institution down in 401. So if we do that, draw my carbon chains. And then there's going to be a carbon D over here. I'm going to switch back to red. My email, my uWindsor email actually sends anything I get from Western directly to spam. That's not me doing it. That's uWindsor's spam filter sending anything from Western directly to spam, which is a problem because I work with people there. So I've got a double bond between carbon C and carbon D. I need to draw that in here. I don't need to adjust my bond angles for that because 120 degrees is the bond angle between things with double bonds. Again, we're going to come back to that. So it's all good. I don't need to worry about that. I've got an OH. I prefer, whenever possible, to continue the zigzag. So I'm going to keep zagging, I guess, here, or zigging. I'm not quite sure which one I'm doing. Then on anything else interesting, well, carbon B's got a fluorine on it. And it's also got an H2. So note I've done two different things with my oxygen and nitrogen. On the oxygen, I actually drew an OH bond. On the nitrogen, I just put two H2s adjacent to it. Shouldn't a carbon with double bond. I'm not numbering my carbons in priority at this point. I'm just trying to draw this out. This is the same as the Lewis structure. So this is that same molecule. I haven't yet assigned any numbering. I haven't yet said which one of these is a priority. If you're looking to name these things, if you've opened up your naming thing and gone back to that, and I hope you did, this is carbon 1 over here. If we were trying to name this, let's name it just because we can. I want to show you how I name these kinds of things. So carbon 1, carbon 2, carbon 3, carbon 4. And this is carbon 1 because it has the most oxygen atom on it. The carbon with the highest oxidation state is always your lowest number. And again, if you need to review that, please take a look in a textbook into how to name these kinds of things. This is the only carbon with an oxygen on it, and so it's automatically, you're trying to get that as low as possible. Luckily, we can make it carbon 1. So what I try and do with these things, I try and figure out what things need to go into the name. Sorry, if the audio is breaking up. Is it breaking up for everybody? Okay, so I think it's on somebody's line. So I need to figure out what things go into the name. So let's make sure we get all the parts. And what you can almost do is cross them out as you get to them. So since this is got an alcohol on it, and the alcohol is the dominant, most important functional group on this molecule, this is a 1-all. That's going to take care of my alcohol. On carbon 3, I've got a 3-amino because there's an amine on it. Carbon 3 also has a 3-fluoro because there's a fluoro on it. carbon 1 has a double bond, so it's an ene. So it's a 1-ene. The molecule has 4 carbons, so that's a bute. And the geometry of the double bond, and we're going to come to this later, I'm going to just basically say that this is a E double bond. If you haven't seen E double bond, don't worry, we are going to get to that later. I'm not going to ask you questions until we cover that. You can write the OH like I wrote the NH2, that is absolutely fine. Because I didn't draw them. That's why the lone pairs on fluorine aren't on there. They should be. You're absolutely right. So those are our components to this molecule. And so if I'm putting this together, I'm going to write it as alphabetical order, 3 amino, 3 fluoro. I'm putting hyphens between letters and numbers. I put commas between 2 numbers. I'm going to put E out front. And it is, I can call this, sure, bute 1 ene 1 all. There's a few different places you could have put the ones at the back there. We're going to come back to the E. Don't worry about the E, Claire. I just want to be right if I'm actually going to write something. We are going to come back to that when we're talking about double bonds a little bit later. What that's basically saying is there's different ways to, the thing about saying butenol is you're not telling me where the ene and the all are. And you can't assume one. So no, you do have to say bute 1 ene 1 all. That is the 1 butenol is okay, but the 1 only refers to the ene. So somebody said, what about 1 butenol? You could write 1 butene 1 all. That would be fine. But the 1 refers to the first functional group in a name, and the first functional group when you wrote butene all is the ene. So this would be fine. All this the same. 1 butene 1 all would also be fully appropriate. But you do need to actually state, and this molecule is not actually stable, and we're going to talk about why it's not stable later. It actually doesn't exist like this. You would never actually draw this. But for naming practice, it's good. Okay. Except for the E, which you guys haven't seen before, a lot of you. That rest of that stuff better, like maybe the way of I constructed writing everything down and crossing stuff out or doing all that, that might be different, but none of those abbreviations should be brand new. If they are brand new, please spend some time on the naming software. You always read left to right. This is, if I was reading this compound out, I would call it E3 amino 3 fluorobutene 1 all, 1 ene 1 all, which is a stupid name. The way the molecule is drawn is irrelevant. No matter how you draw the molecule can be drawn lots and lots of different ways. It can be drawn on its head, it can be drawn flipped around, it can be drawn going into the plane of the page. It's still the same molecule, so it better have the same name. We are going to do a little bit more practicing because we're going to be talking about this E double bond thing, and we're going to be talking about stereochemistry, R and S, and specific enantiomers and stuff. Okay, so these are some of my favorite molecules. So this is tetrodotoxin. If I had a tattoo of anything, I don't have tattoos because I just don't believe in them. Personal choice. Fully fine with all of you guys who are tattooed. But this is a molecule that is in the pufferfish toxin. And so does the order of naming it matter? Yeah, the order matters. So this is the pufferfish toxin. It's the one that you get if you eat like fugu, that's sushi, and you cut into the swim bladder, and then you go numb, and then you die. If you cut it right, you only get a little bit, and your lips go a little bit numb. If you get too much, you die. And so I was involved in making this thing. It was a lot of fun. This is what it looks like in 3 dimensions. It like we draw it out like this, but it's just basically this Kiji thing. And the nice thing is these rules. Okay, thanks, Suhib. Like, it's great, but no, Armla, you do not need to name this thing. That's why nobody names it the official name. I can't name it. I would punch it into a piece of software to spit out the name, but there's a common name. But I just want to show we can represent anything with these line draw structures. This is another kind of molecule that I've made before. I love these kinds of things. So what we've done here is we have this, kind of linear thing. It's actually got a peptide on it. Like this is amino acids making a chain, and it's very, very lipid soluble. It's an oil kind of thing. And then it's got this really well-defined branching sequence. And I've got sugars on the surface. And these are what sugars look like, these things here on the end. And they're really water soluble. And so this thing basically, you stick this molecule into water and it makes nanorobots. It self-assembles itself into a structure. And then it actually freaks out the immune system and gets a really big immune system response. It does look like a genealogy. I can't name either of these. I call this, this is 1, 2, 3. This is the third generation C-glycoside galactose dendron with a polyglutamate of N length on it. Yeah, we tend not to name them when they get too long. We tend to use compound 1. There is an official name for this. I actually have it written down somewhere. It's about 5 lines long, like full across the page. Yeah, it's called dendron because a dendron means tree-like in Greek, and it looks like a tree. You stick this thing right side up and it looks like the branches of a tree. Anyway, naming these is beyond the scope of the course. But what I want to point out is that the conventions we just talked about on how to draw molecules, that is what is used. That is the standard convention. Like there's no deeper level to this. That is how we draw them. I am going to talk a little bit about what all these wedges and dashes and other things mean, because they have definite meaning, but not today. If you need practice converting Lewis dot structures into structures and line draw structures and going back and forth between these things, textbook has some practice problems. It's going to be a review for a lot of you. For some of you, it's not a review. If you have any doubts about interpreting these line angle formula, please practice, because I am going to be using those basically exclusively starting next week. Yeah, these are all on Mobius. So these are all the chapter questions. They're the same ones for the textbook and on Mobius. If you're comfortable with all this, awesome. If you're not, I don't have my camera on. I just gave a double thumbs up. I should probably turn my camera on. Give people something to look at. There we go. Okay. Yeah, of course. Yeah, acetone has a resonance structure. Anything with double bonds has a resonance structure. It's the fun of that. Oh, great. Now the camera's superimposed on my screen. Just shrink it and stick it in the corner or something. Okay. So hopefully by the end of this thing, you can do this. You can convert between Lewis structures, condensed structural formula, and line angle formulas. I'm never going to ask you to do this on an exam. It might be something you have to do on some of the tutorial questions, but it's something that's kind of built into it. If you can't do it, it's like you're trying to, I think I brought up the analogy of a screwdriver. This is your hammer. We're going to go through like the entire toolbox. You need the entire toolbox to be able to build anything with it. And you're not going to understand what I'm saying if you can't follow those line angle formulas. Okay. So I'm going to, yeah, keep them. That would be good. Okay, I'm going to stop recording for a second, and I'm going to start recording